Hi there and welcome from Ventura, California to today's webinar, Security Risks with Commercial Drones. How serious is this risk and what's the latest in detection and mitigation? Sponsored by Inside GNSS, Rohde and Schwarz, and Inside Unmanned Systems, and hosted by WebAttrack, the leader in thought leadership webinars. I'm Lori Dearman, Executive Webinar Producer with WebAttrack, and I will be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the current state of the science in drone defense. We've invited you along with over 300 professionals from 37 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher Inside GNSS, Inside Unmanned Systems, would like to take just a moment to welcome you and introduce General Poss, who will be moderating the main portion of today's webinar. Over to you, Richard.
Thanks so much, Lori. On behalf of the Inside Unmanned Systems and Inside GNSS team, including our editor, Glenn Gibbons, our managing editor, Stan Goff, and myself, I extend a very warm welcome to our international audience for today's web seminar. We're going to hear a fascinating discussion on the critical technologies necessary for assured detection and mitigation of commercial drones. Now, I'd like to turn the webinar over to today's moderator, General Jim Poss. General Poss is the CEO of ISR Ideas, an intelligence, unmanned aerial systems, and cyber warfare consulting firm. He's the founder and former executive director of the Alliance for System Safety of UAS through Research Excellence, which was the FAA Center of Excellence for Unmanned Research. He's a 30-year U.S. Air Force veteran with combat experience in 4 wars and was the Air Force's senior career intelligence officer at his transition from active service in 2013. He's a leading expert on UAS, having helped design the U.S. Air Force's remote split operation systems for UAS control and the distributed common ground station for UAS intelligence analysis. General Poss also has extensive experience in cyber operations from his assignments with the National Security Agency and as the Air Force lead for the stand-up of U.S. Cyber Command. He's also a columnist for Inside Unmanned Systems magazine, and we're very happy to have him with us today. General Poss.
Richard, thank you for that way too kind introduction there. I really appreciate this, and I really appreciate your invitation to run this webinar because it is of great importance in today's 21st century world. Not just what can you do with good drones doing good stuff, but what can you do about bad drones doing bad stuff. So let me just kind of set a set an expectation here. We've got some of the best technical experts on the planet. They're going to be talking about drone detection, a little bit about countermeasures. We won't go a great deal into that because particularly if you're listening from the States, you know that there's a lot of policy prohibitions on what you can and can't do to counter drones. But we're at least going to get you fit into how you can detect bad drones potentially doing bad things to good people. Okay, and I'm gonna hit the next slide here, Lori, and I think we've got a poll question up, don't we?
We sure do, and folks, coming up on your screen is our first poll for today, and we would very much like to hear from each of you on the question, how much do you know about existing counter-drone solutions? I'm just getting started. I know some of the basics about different counter-drone solutions. I have a good overview of the technologies available. Perhaps you have a good overview of the technologies available and tried out some of them.
Let me make my prediction before we start. I noticed that about 25% of the folks were government on there, Lori, of the 300 registered. So I'm going to say most of this is a pretty savvy audience and they know what they're talking about. So that's my prediction.
All right. Well, then let's take a look at those results. So it looks like we've got 43% just started, 35 with some basics, 18 good overview, 4 with overview and tried some. And yeah, there you have it. And any thoughts there, General Poss?
Well, I think we're just going to go right on because I was clearly wrong. And it sounds like we got a lot of folks that are very interested that are starting out. And, and I'll be honest with you, not to make excuses for having blown the prediction, but really, it's been about a year since counter UAS has been front and center in a lot of our governments out there, largely based on what ISIL is doing out in Syria and Iraq. So I was wrong, but for a good reason. Does that make sense? Okay.
All right, we'll take it.
All right. Yeah, we'll take it. All right. So here's our panel today. You've got some of the true experts out there that are going to be able to answer all of your technical questions that know exactly the ins and out of counter UAS detection. But before we start, let me give you a little bit of an intro on what I see as the big problem. I've called it when good drones go bad. So here's some examples of, first and foremost, this is bad drones versus idiots, and most everybody has seen this one. I'm not going to name names, but he's a singer, and that shows why you never touch a drone that is spinning at 3,000 RPM. Here's our next one. Oops. Bad drones versus worse people. Now, I will admit this is Wandsworth Prison in London. My mother's a Londoner. They're all from the East End. Wandsworth is in the West End of London, and that is a drone delivering what I'm assuming is a big bag of caviar that they eat in the West End. God knows what they would deliver to the East End of London. Now here's one that where it starts to get really frightening, and this is again another famous one. This is Dresden, Germany. That is a Parrot drone that is landing, being taken out by a mysterious man in an umbrella. I don't know why he has the umbrella. And who did it land close to but none other than Angela Merkel. And if you don't know Angela Merkel, that smile is someone in security is getting fired smile because it got that close to a world leader. And just imagine if that drone had this. And this is an ordinary DJI Phantom drone that has been configured to drop a rifle grenade with a 3D printed tail on it. That is an Iraqi tank in Mosul. And that is an ISIL operator using the auto hover feature of the DJI to auto hover over the hatch of an M1 tank and drop it right down the hatch. So this, both the Angela Merkel incident and then this incident, which has been going on for about a year in Iraq and Syria with hundreds of attacks on coalition forces, is really why we're here today. So with that said, I'm going to turn this over to Darren McCarthy. That's going to kind of give us an overview of the technology involved. Darren is the Technical Marketing Manager for Aerospace, Defense, and Government Solutions for Rohde and Schwarz in America. He has over 30 years experience in R&D management, and technical marketing in the test and measurement industry. He's published over 50 technical articles on various subject matters across the A&D industry. Over to you, Daryl. Give us an overview.
Thank you very much, General Poss. First, I want to give a brief introduction of who Rohde and Schwarz is. We are a family-owned, privately held German company with over 80 years in a pioneering role in RF engineering. In last fiscal year, we netted over 1.9 billion euro in sales. We have over 10,000 employees worldwide, including 500 in the U.S. In the roles of R&D and system engineering. What we strive for is leadership in innovation and leadership in all of our business areas, including test and measurement, broadcast media, secure communications, monitoring and network testing, where drone detection and counter UAS is part of, as well as cybersecurity. Just give an overview and context of the workflow and what we're talking about with drone defense. Situational awareness and early warning and early detection is very important. We're going to talk a little bit about identification, detection, reducing false alarms, the importance there. Sensor fusion gets into the need for open interfaces. We're going to talk a little bit about the advantages that can be taken with mixed technologies, especially when they can complement one another, and then briefly discuss countermeasures toward the end of the presentation. Just to be upfront about the different types of commercial drones, there's no single detection system that's sufficient to comply with a variety of requirements. We have drones that are commercial that have Wi-Fi control that can be controlled by smartphones or tablets. Those which have data links which are radio controlled and remote control operators. Those definitely have RF input and RF output, so they are actually creating an RF signature that can be seen. There's also waypoint navigation, which are pre-programmed to follow via GPS or GNSS solutions, which can navigate to a point, as well as those which can use inertial navigation. So with this said, there's not a single technology that's effective for 100% of the different types of commercial drones that are out there. So an integrated approach or a multi-sensor fused workflow is very important. And what we're going to talk about today is some of the key technologies involved with sensor technology, including RF sensors, radars, acoustics, and optical. Centralizing that in a control software, integrating the different types of sensors, and then the effectors. I'll briefly talk about the effectors, whether it's jamming, disconnect, or other types of nets or eagle collection. Back to you, General Poss.
All right. Thank you very much, Darren. Okay, Laurie, we have got a second poll coming up here, and seeing as how well I did on the first poll, I'm going to resist making a prediction on this one. What I will tell you is originally when we had this, we asked you to just pick two. Can we pick up to three on this one? Or
Sure
is this
can.
just okay.
Yep.
I say you can only do it with three, but your minus my differ, and I'm going to stay silent given my horrible performance on the first poll.
So folks, you should see on your screen that poll question. What are the most important detection assets of a counter UAS solution? And again, you can pick up to three responses on this one. It looks like we have 69% coming in with radar, 86% RF, 25% acoustic, 60% optical, 5% other. So what are your thoughts there, General Poss?
I think I'm a genius. That's exactly what I would have picked, and I think I will go back to making predictions. So yeah, the panelists either back me up or not, but I just don't see how you can have an effective counter UAS system without at least RF detection, electro-optical IR, and radar on there. And I'm sure the panelists will back me up on this because they're very complementary to each other. I see a lot of single, particularly RF solutions out there, and I just don't think that's an effective way to go about it. But I could be wrong, so let's see what the panelists say. And speaking of panelists, coming to us all the way from Munich, Germany is Getz Maser, who is the Director of Counter UAV Detection and Counter Solutions, working for Rohde and Schwarz in the headquarters in Munich. Getz is responsible for the international counter UAV business of Rohde and Schwarz. Before that, he held several positions as a product and project manager in the secure communications divisions of Rohde and Schwarz. Getz studied electronics at the University of Karlsruhe in Germany on luxurious Autobahn 8, leading to Stuttgart, one of my favorite places in Germany, as is Karlsruhe. Over to you, Getz.
Yes, thank you, General Poss, for the introduction, and a warm welcome from Munich down to the folks on air today. So in this first technology section, we will talk about the technologies and challenges that come along with radio detection of drones. So before we get started, I will talk a little bit about some facts which come with radio controls. So you have to know that 90% of the drones out there are operated in the ISM band via proprietary protocols. Most of them use bad spectrum methods like FHSS or DSSS. Some of them are using Wi-Fi and Bluetooth standard protocols. And you have to know that the radio link is called uplink. This is a link which the controller used to control the drone, and downlink is the thing which is coming back, so telemetry data or video which is coming back from the drone. We have to know that different frequency bands are used. Nearly all of them are in the ISM bands. The 2.4 gigahertz band is used most of the time, but also the 5.8 gigahertz band and rarely the 433 megahertz bands are used. Some outdated frequency bands like 27, 35 or 72 megahertz are hardly used anymore, but please also note that some countries are using specific other bands. So, but what is RF detection all about? So the main advantage of RF detection is that the early warning capability of RF detection. So even if the drone is still on the ground or not in the air, you already get an alarm as soon as the controller is switched on. And that's the big advantage. Another big advantage is that you this is the only sensor which gives you the position of the drone operator and not only the drone. Now let's have a look what are the necessary steps to do RF detection. So first of all, you have to scan the bands. As I told you, different frequency bands are used, and this has to be scanned automatically, and the best select according the scenario you have. Next, the best possible analysis window inside the frequency band has to be found. This is the more important the smaller the real-time bandwidth is compared to the hopper bandwidth of the drone control signal. And next, the signal has to be detected inside this window. Then the signal has to be classified automatically. And this can happen in two different ways. First of all, the spectrum is analyzed at a certain time. This analysis is very complex, but has its limits, as different emitters are using the same channel at the same time. To get an accurate identified signal, you have to take the time into account, and this leads to IQ-based analysis. IQ-based analysis is very complex, but gives you the best possible results in real environments. And in the next step, you classify the signal against matched and predefined profiles, and finally an alarm will be triggered when the drone signal is detected. Let's have a look on the ISM band. Here you see a standard 2.4 gigahertz band. You can easily see some wide and broadband signals out there. You also can see some hopper signals in there. But how does the spectrum really look in real life? If you already think that's a dense signal, dense spectrum, let's have a look at the next slide. And that's a spectrum which you see on the slide now, which was recorded in an urban environment. Can you spot the drone signal here? For sure you will find maybe some Bluetooth and Wi-Fi signals or some wireless video devices, but where is the drone? The drone is still here. And now you can imagine how challenging and complex it is to detect the drone signal in a congested environment. And that's important to keep in mind. On the next slide, I will talk a little bit about the different characteristics of drone signals. First of all, the most obvious one is the center frequency and the bandwidth of the hopper. Next, we are talking about duration of the signal. Here we have typically some 100 microseconds. We have the symbol weight going from kilobaud to megabaud. We have the shift hop weights of several hundred hops and the modulation. And the more criteria you can identify, the better the results are in terms of accurate identification. This allows you to differentiate between similar profiles. And as a result, you get good alarms with low false alarm rates. And this is really important for 24/7 operations. But what are the detection ranges you can expect? It's pretty easy. It's the same range as a drone control link under the same propagation conditions. And these ranges depend mainly on the output power and the frequency bands. So standard remote controls, which are available in the US and in Europe, have an output power which allows you 1 to 2 kilometer ranges. And then depending on the used frequency bands, this is limited. So in the 2.4, we are talking about a maximum of 3 kilometer. In the 5.8, a maximum of 1 kilometer. And the lower bands, like the 430 hertz mega band, allows you several kilometers of ranges. But if we are talking now about different controller types, it's important to also not looking only at the full band toppers, or also partial band toppers and fixed frequency channel drones are important. And this could be a channel, as a chosen analysis window does not contain the signal at all. The automatic classification of all possible drones allow you a categorization. So all drones can be assigned to a whitelist, and only unknown drones are triggering an alarm. And that's also important for a 24/7 operation. Now, let's summarize what is important if we are talking about RF detection. So as I mentioned, it has to work in reliable and real environments. So meaning it has to work in congested and dense environments. And all type of controllers in all bands have to be detected. Very important is also to allow 24/7 operation, and therefore you need a system which can be easily operated, because not the operator will not be a signal analysis expert. Low false alarm rates are very important, otherwise the operator has to jump off the chair every 15 minutes to check if this was really a drone. And last but not least, the classification and the whitelisting reduces the alarms. Last but not least, it is very important to have an expandable system, because with the technology of the drones will be developed further, new frequency bands will be used, and the system gives the user a chance to also create his own profiles. Now we have talked a lot about detection of drone signals. Let me show you one slide and tell a little bit about locating of drone signal. That's also a challenge, because we have very short durations, we have frequency agile systems, we have co-channel interferences, because different signals are used at the same time, and for sure in urban environment we always have multipath propagation. Therefore you need an advanced direction finding system, which gives you fast and automatic direction finding, is immune against reflections, and the direction finding has to be based on pulses, not the channel, because the channel is used from two emitters at the same time. Therefore, you need a two-channel direction finder. For sure, several bearings have to be directed simultaneously, and it should be possible to combine several DFs to get an exact position. Now I'm already coming to the end. So the summary is RF detection is important, because it's the only sensor which gives you early warning and the possibility to locate the operator. And keep in mind, it's important that you have a system that is reliable in real environments, gives you 24/7 operation, and is expandable to in the future. So that was my part. And what you also have to keep in mind, now you can detect all the drones, but what is with autonomous drones? And this will come in the next section. So back to you, General Pause.
Okay, thank you very much, Getz. Okay, we've got our first set of questions next. You know, Getz, not to pick on you because you've been our primary briefer so far, but that was an awful lot of technical stuff that you put out there. Tell me what is really important if I plan to evaluate and test different drone detection solutions. I mean, how do you tell what works and what doesn't?
So yeah, it is very important that you choose a test scenario that is close to your planned target scenario. So it does not make sense to just test the sensor in the lab. So if you have an urban environment, then go out there looking for a congested ISM band and do the tests there. And as mentioned, have a close look at the false alarm rates. Check if the system is able to detect several drones of the same and different types simultaneously, and use controller which have very similar control signals. And if you have all this in mind and do the tests, then you will get out a good RF sensor.
Okay, great answer. Okay, and as predicted, there's a little bit of a war going on the questions between the pro and anti-RF detection, folks. And Getz, I got to tell you right off the bat, as a long-time NSA employee, I'm with you. I think RF is the most important. But generally, what everyone is asking is, and we've kind of answered the question, of what happens if they turn off the data link. But a really good follow-up question was, okay, if they turn off the data link, isn't RF still important? Aren't there a whole bunch of unintended emissions that you could pick up? A lot of times maybe drone operators think they turn the link off, but it's not. I mean, if you've really got somebody that's out to get you and he's turned off the data link and he's flying autonomously, does RF continue to matter? Getz, would you mind taking that? And if anybody else is on the panel has got a thought, please chime in.
Yeah, that's true. So most of the drones out there still, if they are on GPS mode and going through different waypoints, they will send something down to the controller. If the controller is still in line of sight, if not, then it still works, and then we have to have something else. So then we come to other technologies, which will be part of the next section.
Okay, gotcha. Good answer there. There's also seems to be a lot of questions about the ranges, that we listed in there. I did not realize that DJI claims a 5 to 7 mile range on their link. So there's some implication that you should get greater ranges there, Getz. And then there's some others saying that the ranges are much smaller. I mean, how confident are you of your average 1 to 2 kilometer range? Is that conservative or liberal? Getz.
Yeah, as I mentioned, that's just a matter of the output power. So in case of the DJI, they have a booster running, and then you also get also higher ranges. But what is important? So as soon as you can still control the drone, you can also detect the controller, and that's important. And the other is just physics. So nobody can change the physics. So ranges depends on frequency and output power. That's easy physics.
That makes sense. And then we're getting a couple questions that are policy-based questions. Is it legal to listen in and decode RF signals? Is it different for private individuals versus law enforcement? I got to apologize up front. We are just not going to be able to get into the policy questions here. This is a technical webinar on what is technically possible. The short answer for those of you listening in from the States is really the only people that can engage in counter-UAS operations are the Department of Defense, Secret Service when the life of the president is involved, Department of Energy when nuclear facilities are involved. And even having said that, there's still a raging legal battle over who has the right to listen and decode RF signals. It has a lot to do with the wiretapping laws here in the United States. So unfortunately, that's as deep as we can get into the policy side out there. Okay, let me see. Here's another good question. Getz, I know we're giving you kind of a workout here, but all the questions are RF based. How do you deal with somebody that's using multiple false signals, hiding the real drones in flight? If you've got someone that's got a false signal generator out there. I mean, if you got someone that is really out to get you and he puts out a bunch of false signals in addition to the real one, how good are you at sorting false signals from true signals?
Yeah, that's something I mentioned with my recommendation how to test it. So that's a good way to test. Even if you take 2 controllers of the same type of drone, switch them both on and check if the detection, the RF sensor you are using for detection is detecting both of them or just generating one alarm. And that's a good way to test. And if you have a good sensor, then he shall generate 2 alarms, and that makes it very hard to really trick it with false alarms.
Well, that makes sense. But so, this is kind of a follow-up question I got. You see a lot of receivers out there on the market. Some of them look suspiciously cheap. What's your opinion of the level of quality that you've got to have in your receiver system and the whole system in order to make a viable RF detection system, Getz?
Yeah, the range is very wide, from very cheap to very expensive solution. So it's a matter how you do it, what is realized in hardware and software, and what is more important is what kind of receiver is used, what is the real-time bandwidth of the receiver, is it somehow limited to dynamics, and very often also the computer power of the receiver is important because complex IQ signal analysis calculation have to be done. So all this has to be taken into account, and then you can expect different results. That's for sure.
Okay, so quality matters. Okay, and I am getting the hook. Apparently that was all the time we had for our initial questions. Don't worry, we've got time for a whole panel of them next. So without further ado, let's turn it over to Dave Romero. And Dave is a partner at Black Sage and a lifelong entrepreneur who got his start in data science and now works with U.S. and foreign militaries implementing strategies and technology for countering UAS threats. And Dave, I think you're going to give us a different take on what type of sensor we need for counter UAS. So over to you, Dave.
Yes, thank you, General Voss. So in this segment, I'll be discussing using radar as an active detection component in a layered counter UAS system. So unlike the RF detection, a radar is not going to provide the position of the aircraft or the operator before it takes off. But what it will do is provide a detection of all moving objects in the airspace inside of its field of view. And what this means is that we're using the advantage of physics to be able to measure the reflections off of moving objects to be able to have a situational awareness of anything that's currently flying. This is a consideration that we pay in terms of volumes of airspace, and as opposed to a traditional security paradigm where we're thinking in terms of 2 dimensions, we are now shifting that paradigm to threats that fly vertically and to thinking of covering airspace in complete volumes. So in some cases, we're using radars in multiples, and we're using sensors that have large vertical fields of view in addition to covering 360-degree horizontal. And the active detection is going to provide us a characteristic data of every object in its field of view, including objects that are flying at high altitudes, as manually piloted or autonomous UAS can now do, traveling down vertically on top of a point of interest. We can no longer consider security in just 2 dimensions. We've got to consider high-flying threats as well. So here's a quick comparison of 3 different common types of radars using counter UAS. The first is a flat panel pulse Doppler sensor. These have a typical range of 1 kilometers. And to create a 360-degree coverage, we'd use 4 sensors and have a vertical field of view of 20 degrees. The typical cost of this 360-degree coverage would be around $150,000 US. The next sensor is a flat panel electronically scanned array. While having a slightly shorter range at 700 meters, this has a 360-degree by 80-degree vertical field of view, which means that we have almost a complete hemisphere of coverage. And these sensors for that complete 360 are about 120 USD. And then you get into much longer range sensors. We're talking about rotating electronically scanned arrays. These are almost an order of magnitude longer range, a detection range of 7 kilometers with a complete diameter of 14 kilometers. So if you think about the volume, it's a massive amount. And on sensors like this, we can expect full horizontal coverage with the spinning of the sensor at 360 degrees and complete vertical coverage, a complete hemisphere at 90 degrees vertical coverage. These are heavy. They're also very expensive. But these 3 different sensors can be combined into a system that can do things like contour urban environments, using different panels to cover urban canyons, and to be able to scale across very large complex sites where smaller panels are necessary. So why use radars for counter UAS? There are 2 primary reasons. One is because they provide the active detection of moving objects in the scene, birds, fixed wing, manned aircraft, UAS, and they provide the accurate position of that object. So radars are giving us a horizontal angle from the sensor, a vertical angle from the sensor, and those are extrapolated into latitude, longitude, and altitude. And we can do a lot of neat things using that accurate 3D position along with the characteristic data provided by each detection. So if we look at a radar detection, what we're searching for is the highest quality data possible and the greatest number of characteristics that come from the sensor. And typically radars will provide radar cross-section. This is an approximation of the reflective surface area of a target. They'll provide range, that horizontal angle from the sensor, vertical angle. And over time, as we get detections in, sometimes 1 per second, sometimes 1 every 5 seconds, we use that time component to calculate other characteristics that help build a very strong signature or unique profile of a moving object. These are characteristics like total displacement from its starting position, acceleration, velocity, and many more. And all these characteristics combined, they give us this signature that allow us to differentiate different classes of moving objects, to be able to differentiate a UAS from a bird, for example. So in order to effectively classify a target, we're looking for as much data as we can possibly receive from a sensor. There are sensors out that will provide updates at more than 1 time per second. When these detections come through, all the detections and the characteristics are passed through a what we call a target classifier. The flavor that we use is an artificial neural network, and these neural networks are trained to recognize multiple types of moving objects. And when new detections are passed through these classifiers, the classifier will produce the probability that this detection belongs to any of the existing pre-trained classes. And these probabilities are in the form of percentages. So a detection, it will report being, for example, 80% likely to be a UAS and 20% likely to be a bird. And so this introduces a major difference from a traditional deterministic threshold alarm. The old way of doing things is taking a characteristic like radar cross-section, setting a minimum value and a maximum value, and then triggering an alarm based on that range. And the trouble with false alarms and security in general is that in order to not miss the things that are most important, we have the natural tendency to expand those minimums and maximums because we cannot risk a catastrophic event. When we expand those, we dramatically increase the rate of false alarms, and that's what we call the boy who cried wolf problem. So using a target classifier, a probabilistic system, that's combined with a deterministic system, and now we can set alarms based on a percentage threshold being reached. For example, anything greater than 80% likely to be a drone, take action. So part of using classifiers is also making sure that operators are confident in their performance. And what we look at is what is the accuracy of the probabilities that a classifier is producing. And the way that works is that every time a classifier is generated, when any new training data comes into that classifier, whether it's generated by the operator or part of the pre-trained set of detections that it was trained on, it's going to automatically go through a cross-validation process. And this uses an objective statistical technique. It generates what you see on the right side of the screen. We call this a receiver operating characteristic curve. And this curve tells us exactly how that classifier is producing probabilities based on how it was trained. And we do this multiple times. We average out the accuracies of each cross-validation, and then we report that back to the operator so that they know when they use the classifier to trigger actions in the system, that it's 85% accurate or 90% accurate, that gives them the confidence to use some more intelligent processes for triggering alarms. So another aspect of a good counter-UAS radar is being able to provide accurate 3D position of a remote object. When we have the benefits of classification and the benefit of precise positions that come from the sensor in the form of latitude, longitude, and altitude, we can then intelligently allocate many other counter-UAS assets. In the picture, you can see that we've got a 18 million candle power illuminator, a UAS jammer, a couple cameras. When there's a target in the field of view of our radars, we want the ability to automatically slew these effectors on target, these cameras on target. And these positioners that we mount effectors on, these can be scaled across large sites in multiples. And when we do that, we're automatically drawing an imaginary line from our target that triggered an action in the system down to the positioner. And then for each positioner, we will automatically set the tilt angle and the horizontal angle according to that imaginary line to keep those positioners on target as that object moves and as we get new detections from the sensor. So automatic slew to queue, that imaginary line, we call that geopointing. That is a core component about being able to scale effectors across large sites. When we use multiple positioners, multiple effectors, we have to rely on good radar data. That good data is then what allows us to prioritize multiple threats. We do that with software. We automatically give each positioner a job to enable it to effectively divide tasks across a larger system. And then finally, the shortcomings of radar. When we're depending on radar to automatically point effectors, our ability to take action on detections is limited by the number of detections that sensors are producing. And this means that if we're getting one detection every several seconds, we're only going to be able to update the positions of our hand tilt motors on every detection. And that has some negative consequences, meaning that in some cases, if we have directed energy or say, for example, an illuminator, we're only going to have energy on target for a certain part of the time while we're waiting for the next detection to come in. And that's going to lead in nicely to the next discussion on video tracking. That's it for radar. Back to you, General Pass.
All right. Thank you very much, Dave. Okay. Ooh, sounds like radar is pretty important, but we do have one last major sensor sector to go into before we can start making our mind up on what works and what doesn't for counter UAS. And luckily, we've got Ross Lamb, who is a partner at Black Sage Technology. He obtained his PhD in engineering from UC Davis, which is one of our Assure FAA Center of Excellence schools, with a concentration in image processing and machine vision. Ross has focused his energy for the past 17 years working with long-range video tracking and electro-optical infrared camera systems. So over to you, Ross. Convince us that we got to have EO and IR.
All right. Thank you very much, General Pass. So let's get right into it. So what we're hopefully going to address in this portion of the discussion is, why would we want cameras in counter UAS? What can cameras do that some of the other sensors don't do? We'll also speak to what the shortcomings of cameras are in counter UAS, which will lead, hopefully, to this supporting the concept that we really need this layered approach in countering drones. So first, the shortcomings of camera systems. What cameras are not really great at is covering this large area for early warning or 360-degree detection of the drones. Cameras are really good at pinpointing, zooming in, and looking at long distance, but the early warning and the with RF detection and the kind of things that radar can do is not what cameras can do, but This is why we want the layered approach. In this slide here, what we have is a thermal image that is being cued by a radar, and we can see that there is an object over here off to the side. It's actually not in the center of the field of view, and this is partially due to radar's accuracy. We generally see plus or minus 1 or plus or minus 3 degrees of accuracy in pointing, and so we can't zoom the camera in with radar cueing alone in this case. Otherwise it would be outside of the image field of view. And it's important to note that, I can see that there's an object here in the image, but I can't really tell if it's a bird or a drone, if there might be a dangerous payload or not underneath. It's not clear with this level of zoom. Fortunately, with camera systems, we have really great optics available to us, and we can zoom in almost like well, not almost, but precisely like a telescope, and we can put a whole bunch of targets, pixels on target at long range. And so here's an example of a camera that we use for our extreme long range system. It has an 825 millimeter lens on it, and what this means is we can actually produce a 0.6 degree field of view. When we zoom in very narrow, we're looking at the object at up to 3 kilometers for a traditional phantom-sized drone when we have that 0.6 degree field of view image. So that's great if we have a stationary target. We can just use the camera, zoom in on it, and we can see what it is, identify it. But the problem lies in when you have a moving target. And when you have a moving target out at long range, it becomes very cumbersome for an operator to manually control a joystick to follow an object. So what we really need when we zoom in and look through that telescope style view of the image, we need something called video target tracking. And so what is video target tracking? Video tracking is where we are analyzing, we're using software or hardware to analyze each individual image. Traditional imagery comes in 30 times per second. So at that rate, 30 times per second, we're analyzing the image, finding the object of interest in the image, and then we calculate commands to the motors of the pan and tilt that the camera is sitting on, or the positioner, and we automatically steer the camera system aggressively to follow that object. So what we're coming down to is what are the real advantages of camera systems and in counter UAS. And the first one is really where we can have visual identification. It's really important, the previous technologies that we talked about do have some forms of, or do have forms of identification, but with a camera system, we can actually get eyes on target, and we can actually visually determine, is it a drone versus a bird, is there a dangerous payload or not, and oftentimes visual identification is required to allow the use of any sort of countermeasures. The second benefit with cameras and along with video tracking is the ability to really accurately point the effectors. So if we have a high-powered spotlight, if we have some other form of effector such as a jammer, even though those devices might have, in the case of a jammer, a 30-degree cone width, we actually get much more energy if we point it very precisely. We can extend the range of the system. So here's a video on the left side here of us tracking a drone using video tracking. The video is a little bit choppy on the web here. It's not displaying at 30 hertz, but it is operating at 30 hertz in real time. And we're following that object even though it's moving in different directions aggressively. And in fact, you can see in this video, not only is that a drone versus a bird, you can actually even tell that's a phantom style drone, and there is, from what I can tell, there's no dangerous payload underneath. So this is a lot of information for people to be able to take action and make decisions upon. So in this next slide, we're showing the other example of being able to direct effectors very precisely. On the right side, you see the high-powered spotlight pointing right up at that drone, so we're getting all that energy on target. And then in this video that's playing over here, we have the video tracking camera system here on the top right. and then we have wherever the camera is pointed as it tracks that drone moving back and forth, we're slaving the pan and tilt motors of this positioner on the left, which has these directional antennas, which we can then put energy on target. So like I said, having the video tracking with the camera system, we're able to point very accurately, and this allows us to extend the useful range of our effectors. In this case, we have a 18 million candle power spotlight on the right side here, and then we have our tri-band directional and jammer that we have used that has various different Wi-Fi and GPS jamming capabilities. So with this slide, I'm not going to talk in detail, but there are several different kinds of cameras technologies that we've used. Traditional daylight camera systems, otherwise known as electro-optical, EO, is good at using for detecting or for tracking drones out at long range, but more commonly we're looking at long-wave infrared or mid-wave infrared. There are benefits and detriments to these different kinds of infrared imagery, not really meant for this discussion here, but we can talk about that offline if anyone has questions about that. Here's a comparison of some of the different camera systems that we've utilized. Here in the top left we have a 100 millimeter camera system, a long-wave infrared, otherwise known as uncooled. With this kind of camera and lens combination, we under good, reasonable conditions, we see the standard Phantom style drone at about half a kilometer. Then we have our 300 millimeter mid-wave IR, which is a cooled camera system, and we're commonly seeing drones out at a distance of about 1 kilometer under reasonable conditions. And then, as I already mentioned before, we have our 825 millimeter camera system that's a mid-wave IR, and we actually are able to see drones out at 3 kilometers, which is really an amazing thing for that size of an object. And you can see comparative cost for such technologies on the far right here. So one benefit of using thermal, either long wave or mid wave, is that the objects really tend to pop out in the imagery, where we can see when we're cued by the radar in this top image here, we're automatically cueing at one time per second in this scenario, and the object of interest, which I can't really tell exactly what it is in that piece of the image, but there is something of interest that is moving, and so what we can do is we can lock on with video tracking, zoom in, and that helps us produce the image below, where we can really look at that drone, determine what it is, and see if there's a dangerous payload or not underneath. So, in summary, first of all, we already talked about camera systems not really being good at wide area situational awareness or what the early warning and radar systems can do. But what they really are good at, cameras are good at pinpointing on distant targets, so we can do really two things: the visual identification, and then also additionally pointing effectors very accurately with a 30 hertz update on the system. So that's the end of this piece. Back to you, General Paas.
All right. Thank you very much, Ross, for a very convincing presentation. Okay, so we've already introduced Darren, and he's going to get up and tell us very shortly about something that's not really the subject of this webinar. We're sticking mainly on detection, but he's going to give us a quick blurb on what you can do to actually counter UAS. So over to you, Darren.
Thank you very much, General Paas. I think we did a good job of lining up with the first poll questions and talking about some of the most important detection aspects in RF, direction finding, EO, IR, and radar. So I think we had a fortune of having the right panelists on here. I'm going to very briefly talk about mitigation situations, and I guess as in the overall workflow, when you talk about mitigation, the classic answer is depends on the situation, the circumstances, sir. Smart jamming. Smart jamming works well when it can be highly integrated with the detection and identification systems, using technologies such as follower jammer to enable a selection of targeted drones to be jammed while leaving other signals unaffected. We talked previously about whitelist versus blacklist drones. This is a opposed to barrage jamming, which has typically been used, which basically takes out all signals and can have unintended consequences, especially if you intend to operate a drone in the same area. GNSS jamming, again, you can have unintended consequences with PNT and other classifications. Laser, EMP, we talk about some others, the net guns, eagles, spotlights. These mitigation techniques tend to be open issues of national policy and legality of use by civil environments, and primarily the subject of closed discussions. So as we're not talking about policy, that's all we're really going to say about mitigation technologies. These can be closed discussions as follow-up if anybody has requests more information on this. Back to you, General Poss.
All right, thank you very much. And I feel kind of bad about not getting into some of the big questions, which is, what can you do about drones when you do detect them, and who could do it? But that's just, that's probably 4 or 5 other webinars out there, and there was enough information on this one. And speaking about enough information on this one, I realized this was an awful lot of stuff. You can go to our website to get a copy of the presentation here, but more importantly, you can go to the Rohde and Schwarz website to find out about this presentation, download a white paper on Ardronis, which is their name, overall name for counter UAS systems at the Ardronis Learning Center. Okay, we're getting some really good questions here, and hopefully we've got time for quite a few of them. But the first question I get to ask, because I'm the guy controlling the questions, and it's my question. All right, Getz, I'm going to start with you because, again, I'm a former signals intelligence officer, and I think you've got the best answer here. But let's say that you got a limited budget, and you can only pick 2 amongst the winners of our current poll, which is RF detection, radar, and optical/IR. You can only pick 2 of those, Getz. Which 2 would you pick? And then I'll ask Dave and Ross to chime in.
So in that case, I would pick a radar because it gets you the every drone up in the sky, and as a second sensor, I would take an RF sensor because then you get earliest possible warning for at least 90% of the existing drones. That's my answer.
Okay, so radar and RF. So Dave, I think you're going to agree with that, but do you?
Yeah, well, I think, the early parts of the counter-UAS process, the early warning and the active detection, I think those are well matched. I think the early warning provides an increase in operator vigilance, and I think that leads in well to an operator being able to apply that vigilance to then waiting for detections in actively monitored airspace.
Okay, that makes sense. All right, Ross, do you have a different opinion?
All right, well, I'm the odd man out here, but honestly, I think I'm going to agree that radar and early warning detection are, if you have to choose 2, I do think that those are critical ones. Honestly, I do think all 3 forms of all 3 are the best, but if I had to choose 2, which you are making the rules, I think I would go along with that.
Okay, yeah, and that was a stupid rule. You really do need 3, and I think you guys would agree with me on that. So, okay, all right, let's get back into some of these great questions here. So, Dave, can you give us some idea of what a false alarm rate would be in a realistic operating environment? Let's pick one of my favorite airfields, Frankfurt International, because they have actual grocery stores in there. If you're Frankfurt,
okay,
what's your false alarm?
So, first of all, we want to have a clean environment, and for us that also has to do not only with the existing RF in the environment and the possible channel conflicts and reflections, but also making sure that if we're using these radars for an aerial application designed to detect UAS, we want to have those radars pointed in a way that there aren't going to be forms of clutter, whether it's the tops of trees blowing in the wind or flagpoles with flags that kick up, when the wind does. So that's a start, and that's already is going to dramatically reduce the false alarm rate by sheerly reducing the clutter. When it comes to automatic target classification, we are generally shooting for above 90% accuracy, and that percentage, that tells us the ratio of accurate predictions that the classifier is making. So if it makes 100 predictions, that means that 90 are going to be correct and that 10 are going to be incorrect. And this depends site by site. We have to ensure that we have, again, a clean environment, reduction of clutter, that we have a well-trained classifier, meaning that we haven't made mistakes. Accidentally classifying a bird as a drone can really confuse a classifier. So to answer the question, 90% or better. We have sites where we're achieving well above 90%, some where we're performing lower. So it is variable, and that is partially the onus of the system, but also on the operator to ensure that they continue to reinforce it.
All right, 90%, not bad. Okay, and Getz, I'm going to pick on you again, showing the importance of signals intelligence here, just because we've gotten a bunch of questions on this. Okay, so your RF detection scheme, it sounds like, particularly when you're talking about classifying, that you're going to rely on a data link signature library. How do you keep that up to date? I mean, do you expect the manufacturers to turn over signatures to you? You know, and even if they do, a lot of times their signatures that they give you don't look the same in the environment. I mean, isn't keeping a data link library a massive task and potentially a weak spot with RF detection?
Yeah, that's fully right. It is a mess. So, and yeah, the drone vendors will not give us the signatures they have. And it's much worse. They change it from model to model. Some of them are very specialist, like DJI is doing that on a frequent base. We are watching the market and doing updates of our drone profile libraries 3 to 4 times a year, which are then rolled out to our customers. But additional to that, because we could not keep up with all the drones out there worldwide, we give the user itself an easy possibility to generate his own profiles. And that's our answer to that.
That sounds good. Now here's another good one. You know, we've been talking about, you know, ranges as far as in the horizontal ranges. Is there a ceiling on these systems? In other words, if someone's going to come in from, you know, 5,000 feet, 10,000 feet, which they could do, can you detect a higher altitude target? Dave, I think you're best to handle this one.
Yeah, well, this speaks to the you know, the need for volumetric coverage. To cover a high altitude threat that's coming straight down on top of a site, then you need a full 90-degree vertical coverage. And that is achievable with both the small flat panel radars and with the large rotating radars. So there are a variety of options, but yes, that's possible out to 7 kilometers as far as any sensor that we know in the counter UAS market.
Okay, well, that sounds like a great question. Okay, another one we're getting, and I think we covered it. Maybe we didn't cover it well enough in the webinar, but we're getting a lot of questions about how much operator manual effort is required for optical spotting and tracking, how much training is required. Seeing as how we mentioned optical, Ross, could you handle that one for us?
Yes, absolutely. So the way we handle the transition from radar queuing to video tracking, we call it semi-automatic at this point, where we're doing the positioning update based on the radar, but then in order to go and lock in on the target, we have an operator in the loop at this point to zoom in and pull the trigger, if you will. There is some user learning curve to this. Generally, operators are relatively proficient at this within a couple of minutes or an hour's worth of training. It's a very steep learning curve. People are proficient very quickly, and generally it takes only a few seconds. Once there's a radar detection that comes in and we're queuing, it takes a proficient operator just a few seconds to be able to lock onto that target.
Well, that sounds great. I tell you what, back to Getz again. We got a question on what do you do if you've got a drone that is using a data link that's just flat out in your library, not in your library. In a follow-up one, is there anything you can do if they come out of a band that's not generally used by drones? Let's say low VHF or HF. Is there anything you can do about that, Getz?
Yeah, first of all, if the signal turns up, which is not in the library, it will generate an unknown alarm signal. And then you can decide if you have, for example, the second sensor in place, a radar, for example, which is saying, yeah, that's a drone, then you just record this unknown signal and say, okay, that's a drone. So the creation of signals is very, very simple. The second question you had was concerning other frequency bands. Here, the system we have is very flexible. For sure, if you're covering VHF or HF bands, you have to have additional antennas in place, but the receivers are very general and can cover high frequency ranges. So it's possible to adapt our systems to other frequency ranges.
That's great. So I guess it just depends on how likely you think the threat is of an HF data link out there and whether you put the antenna on there or not. Okay, Getz, I'm not going to let you off the stage just yet. I've got one, and it's kind of a pet question of mine. I think you've been following the remote identification or electronic identification of UAS that we're shooting for both in Europe and the United States. If we do really get an electronic identification that gives the geographic position, speed, altitude, heading of the platform, identity of the pilot, location of the ground station, do we really need RF detection systems anymore?
It will make the life much easier, but at least the regulation here in Europe will demand remote IDs only for drones in a certain weight class. So I don't know how the regulations will be in the US, but in Europe it will only for certain drones. And furthermore, the remote ID transponders will be the first thing the really bad guys are getting rid of. So this has to be kept in mind. So I think also with the upcoming remote IDs, there will be a need for remote detection of RF control drones. Okay,
that's a really good point. Bad guys are generally not going to broadcast their position. So in that case, if you were to get a RF detection but not an RFID, that would be your biggest danger sign. Okay, that sounds good. All right, Ross, we got some folks picking on you. What about if it's raining? Is electro-optical or IR any good in the rain or fog or snow, or I guess in Europe generally?
Yeah, so weather definitely can affect the range capability of the system. So the answer is cameras are still effective in inclement weather, but we generally see a reduction in the range at the long range end of that.
What would you consider to be long range?
Well, it depends on the sensor. So when I had that slide up with the different kinds of sensors, we had a short range, a medium range, and a long range system. And in each case, I think we had a 0.5 kilometer, 1 kilometer, and 3 kilometers for detection and tracking under good conditions. And good conditions can be both cloudless or cloudy skies. What's more difficult is when we have a combination of what I refer to as broken clouds or silver-lined clouds. This becomes a little bit more difficult. And so what we do with any one of those three sensors, we kind of expect to see a reduction in their range, in their respective ranges. And I'm not going to give you a specific number because it depends on the actual weather. But with rain, snow, and fog, this is harder for any sort of optical sensor to see through.
Okay, well that certainly makes sense. We're getting another bunch of questions here, and I think, Ross, you're probably the best guy for this one, but let's say an adversary takes, kind of a saturation approach, and I know we're working on that in the military, and, let's say you've got 5 or 6 drones coming in from the same quadrant. I mean, I guess this is kind of a Ross and Dave question. between the radar and the electro-optical stuff, just how would you do that if you had 5 or 6 targets coming from the same quadrant? You've only got, I think the radar would handle it, but how would you do the classification of that attack?
Dave,
so Ross, if you don't mind, I'll start on this one since radar is earlier in the process. The typical radar is going to be able to take in data on many moving objects at once, so there won't be a limitation on detecting 5 objects. Now, depending on the number of positioners used on that site that are going to point effectors, jammers, illuminators, etc., there is a general one-to-one relationship from target to a positioner, meaning we can only point at one thing at a time. And so if there's one positioner and 5 threats, then that positioner is going to be assigned a job. We call these prioritization schemes. And what that looks like is that we can tell it to focus on the thing that is the closest, that meets a certain probability of being a threat, UAS. Or we can tell it to focus on the fastest thing. And this same, applying jobs to positioners can be scaled out. So if we want 5 positioners pointing at each of those, we may give them all the same job, but they're going to divide those tasks being aware of what each other is pointing at to be able to then handle multiple simultaneous threats without having to split time. And then, Ross, anything else?
No, I think you addressed that really well, Dave. Just to reiterate, the radar is monitoring all of those contacts simultaneously, and with multiple positioners, we, like Dave said, prioritization is really a key element to being able to split up the tasks. In this case, the video tracking, we're only going to lock on to one target at a time, and so that's why having multiple camera systems to be able to handle multiple targets is a consideration.
Great answer, and we've only got time for the last question, so this is the last one, and it kind of goes to the heart of what I spent most of my adult life doing, which is sneaking through enemy air defenses. So it seems like, particularly dealing with low radar signature, relatively low RF signature drones coming at a low altitude, that you would have to do a great deal of preparation before you decide where to put your sensors out there. How important is it to do preparation to make sure that you're not masked by buildings or terrain, and to employ kind of a network system approach to where you can put gap filler radars or RF detectors in places where you have problems? How important is that? I think this is kind of a question for everybody. So Dave, you want to start off with it?
Sure. Well, speaking to placement of sensors, I think starting out, being familiar with the site and the physical limitations of the various sensors that are being applied is significant, because when you know the limitations, then you can choose the right tools for the job. There are a wide variety of different variations in each of these modalities that we spoke of, RF detection, active detection with radar, and then optical. And so on a given site, there is going to be a subset of those, different variants that make more sense than the others, oftentimes based on physical limitations. For example, Getz mentioned, urban areas and multipaths. In radar, we deal with the same problems with radar reflections, channel conflicts, and environments that have a lot of other RF transmitters. And I think I'll maybe pass to Getz for more opinion.
I fully agree, Dave. It's all about a site survey doing up front. So have a look at the area to protect, look from where the drones will come, and then find the right positions for the sensors. This is crucial to have the system working really and have good performance.
All right, that sounds good. So
And I would just add in real quick there that every different location is really different, and we've seen set up in urban environments as well as out in desert environments, and there's different sensors, there's different radars, different cameras to select from, and I would say that the question of placement and architecting the appropriate sensors and locations is almost the most important question to answer when you're addressing a new site and fulfilling a site survey for a good installation.
Okay, so don't just walk out at the end of the runway and plunk one of these things down. It's harder than that. All right, gotcha. Hey, a couple other quick questions. We had a bunch of people talking about electronic ID, remote ID, and whether that's going to be mandatory to put that on drones. Can't answer that yet, at least not in the United States. We're just studying that on an FAA aviation rulemaking committee. And then I got a question about whether we're going to send links on email to download all of this presentation. And yes, we are. And with that, Lori, I think this wraps up the webinar. I actually learned a lot. I know there's a tremendous amount to counter UAS. We only handled a portion of it, but we handled a particularly important part of it, which is the detection, which is very hard given the nature of the targets that we're dealing with. So I think our panelists did a great job of telling us what works, and more importantly, what doesn't work. So back to you, Lori.
All right. Well, thank you so much, General Poss. And folks, before we do sign off today, I would like to thank each of you for joining us and trust that you found today's webinar to be of value. Special thanks to our distinguished panel members and, of course, our sponsors, Rohde and Schwarz, and co-hosts Inside GNSS and Inside Unmanned Systems. Again, thanks for joining us. And this is Lori Dearman saying, hope we see you on the next one. Bye for now.